Okay, section 20.3 is about half-life. For decay reactions, then the reaction rate we will call activity. That's what radioactivity is. It's the activity of radiation, or the rate at which radioactive particles are produced and emitted. And the activity depends only on one thing. There is a rate constant and n, or the number of nuclides present. So this is really similar to the first order rate kinetics we saw earlier. It said that rate is equal to K times the concentration of one of the reactants. So here, instead of a molar concentration, we're just going to count the number of nuclides present. That could be in terms of moles or in terms of atoms. And just as long as the rate constant reflected that, that would be fine. It could also be in terms of grams, because the number of moles is always proportional to the mass in grams. Then as long as you're working a simple problem, then you could just use the grams outright. We're not going to be solving for those rate constants. This isn't about kinetics. We did that a couple of chapters ago. So we're going to look at just some really neat, simple little ways to deal with the reaction rates. So it is a first order kinetics problem. And you may recall that first order kinetics has this thing called a half-life. Technically, it's equal to the natural log of 2 over that rate constant. But that's the amount of time it takes for half of your reactant to react away, or in this case, to decay through radiation. So let's look at some half-lives of relevant radioactive materials. So U-238, this is the less radioactive isotope of uranium. It's 4.47 billion years half-life. U-235 is the uranium that we'll talk about tomorrow in terms of nuclear weapons and nuclear power plants. It actually has a very long half-life as well, 704 million years. Carbon-14 is relevant in carbon dating. It has a half-life of almost 6,000 years. Potassium is also used for dating mineral samples, and it has a half-life of about 1 billion years. And then a bunch that have shorter half-lives: strontium at 28 years, tritium at 12.3 years. You may have heard of like compasses and watches that have glow-in-the-dark paint on their needles. Only this glow-in-the-dark paint doesn't need to be recharged in the sun. It works in the dark. It will continue working in the dark for about 12.3 years because it's actually the glow-in-the-dark paint is impregnated with tritium, which will sort of recharge it through its radioactive decay. And to be fair, in 12.3 years it'll just be half as dim. It will still continue glowing, albeit weakly, well beyond that. You've got, that's thorium, two different isotopes of thorium, one of which lasts a mere 25.6 hours and the other one lasts 14 billion years. And then iodine, 131, has a half-life of 8 days. And iodine is kind of an important byproduct of other nuclear reactions. That makes it really important. Those people that are involved in nuclear accidents, say people that were near Fukushima, Japan a few years back, or near Chernobyl in Ukraine many decades ago, iodine was a byproduct of those accidents. And because iodine is absorbed into the body and it is very active with such a short half-life, then one of the things, one of the medical interventions that you do is to give someone just heaps and heaps of iodine in the hopes that non-radioactive isotopes will rapidly replace the radioactive ones, and you can kind of purge your body of that I-131. Anyway, and there's lanthanum. I shouldn't have spent so much time on this, but you'll notice some are alpha emitters, some are beta emitters. The alpha emitters on this table seem to have the longest half-lives. I don't know if that's a coincidence or not, but those are some of the half-lives. Okay, so we looked at the first order integrated rate law back in our kinetics chapter, but there's a slightly different form of it that is really framed around the concept of a half-life that is going to be really useful to us when dealing with radioactivity. Okay, so it says that the natural log of n naught over n is equal to the natural log of 2 over the half-life times T. So this is the amount of radioactive material at the beginning. This is the amount that remains after a certain time has passed, and that is the time. And so this that's the half-life. And this allows us, I don't know if you recall when we talked about kinetics, we kind of danced around the question of how much will be remaining at intervals that are not equal to 1 half-life or 2 half-life or 3 half-lives. Well, this equation will let us find out how much remains at any time at all, whether it's a half-life or not. There's the PDF viewer. All right, so we have a 10-gram sample of that iodine-131. Its half-life is 8 days, and it's left out for 2 weeks. How many grams will remain? So we'll just put this in here, the natural log of it's 10 grams, right there. That's how much we started with, 10.0 grams. And how much remains is our unknown. That's the amount that is at the end. And then the natural log of 2. The half-life is 8 days. And the time that has elapsed is going to be 2 weeks. We better express it in terms of days so that it will cancel out units here. So that would be 14 days. 14 days is longer than 1 half-life, but a little bit less than 2 half-lives. So you might expect it to be something greater than 0.25 grams, but less than 0.5 grams. Anyway, when you solve this, hold on a sec, I'm trying to remember if I have the intermediate numbers. I don't, so I'll go ahead and I've got the solution there, you can see it on the oh, I do have the intermediate part. I'm so sorry. Okay, so in the end, what you can do is you can change this into a negative and invert these two. That'll make it a little easier to put the X on top and the 10.0 grams right there. And so X over 10.0 grams is going to equal, the natural log of that is going to equal negative 1.213. Negative 1.213. So that's natural log of 2 divided by 8 times 14 and a negative. And then we'll raise e to that power, raise e to that power. Raising e to the power gets rid of the natural log, and then we just need to multiply that answer by 10. E raised to the power of negative 1.21 times 10. Anyway, times 10.0 grams to get rid of the 10 over here. And in the end, what we get is 2.97 grams. 2.97 grams. So 2.97 grams is how much remains. It's pretty close to 1/4 of the initial amount because we're pretty close to 2 half-lives, but not quite there yet. Okay, let me... There it goes. All right. And we can take this equation here and rearrange it just a little bit. If we want to figure out how much time is required to pass in order to reach a certain amount of radioactive material left over, we can just rearrange this to be T is going to be equal to natural log of N naught over N times the half-life over the natural log of 2. Okay, and that's just what you get when you flip this over and bring it over to the other side. And so this is maybe a slightly more convenient form of that equation for answering questions like this one. Okay, so strontium-90 has a half-life of 28.8 years. How long does it take for a strontium-90 sample to decay to 1/3 of its initial amount? So we're going to say T is equal to the natural log. Well, I didn't give you any amounts. I said 1/3 of its initial amount. And the great thing about first-order kinetics is that you'll get the same answer whether you have a milligram of strontium-90 or whether you have a kilogram or a ton, a metric ton of strontium-90. It'll be the same answer. All we need to know is that the initial amount is 3 times the amount after the time has passed. So you could say that that's 3n and this is 1n because after the time has passed, it's decayed to 1/3 of the initial amount. And anyway, those would cancel, and so this ends up just being the natural log of 3 times the half-life, which was 28.8 years. 28.8 years over the natural log of 2. Okay, and this works out to be 45.6 years. 45.6 years for strontium-90 to decay to 1/3 of its original amount. Okay, so we'll take these equations and we'll apply them in a very practical way in the next section.